Hello and welcome to this lecture. In this lecture, we will discuss about one solution based on CNI, in particular, Weaveworks. The Weaveworks Weave CNI plugin. In the previous practice test, we saw how it is configured. Now, we will see more details about how it works. We will start where we left off in the pod networking concept section. We had our own custom CNI script that we built and integrated into Kubelet through CNI. In the previous lecture, we saw how, instead of our own custom script, we integrated the Weave plugin. Let us now see how the Weave solution works, as it is important to understand at least one solution well. You should then be able to relate this to other solutions as well. So the networking solution we set up manually had a routing table which mapped what networks are on what hosts. So when a packet is sent from one pod to the other, it goes out to the network, to the router, and finds its way to the node that hosts that pod. Now that works for a small environment and in a simple network. But in larger environments with hundreds of nodes in a cluster and hundreds of pods on each node, this is not practical. The routing table may not support so many entries, and that is where you need to get creative and look for other solutions. Think of the Kubernetes cluster as our company, and the nodes as different office sites. With each site, we have different departments, and within each department, we have different offices. Someone in Office 1 wants to send a packet to Office 3 and hands it over to the office boy. All he knows is it needs to go to Office 3, and he doesn't care who or how it is transported. The office boy takes the package, gets in his car, looks up the address for the target office in GPS, uses directions on the streets, and finds his way to the destination site. Delivers the package to the payroll department, who in turn forwards the package to Office 3. This works just fine for now. We soon expand to different regions and countries, and this process no longer works. It's hard for the office boy to keep track of so many routes to these large number of offices across different countries, and of course he can't drive to these offices by himself. That's where we decide to outsource all mailing and shipping activities to a company who does it best. Once the shipping company is engaged, the first thing that they do is place their agents in each of our company's sites. These agents are responsible for managing all shipping activities between sites. They also keep talking to each other and are well connected. So they all know about each other's sites, the departments in them, and the offices in them. And so when a package is sent from, say, Office 10 to Office 3, the shipping agent in that site intercepts the package and looks at the target office name. He knows exactly in which site and department that office is in through his little internal network with his peers on the other sides. He then places this package into his own new package with the destination address set to the target site's location, and then sends the package through. Once the package arrives at the destination, it is again intercepted by the agent on that site. He opens the packet, retrieves the original packet, and delivers it to the right department. Back to our world, where the Weave CNI plugin is deployed on a cluster, it deploys an agent or service on each node. They communicate with each other to exchange information regarding the nodes and networks and pods within them. Each agent or peer stores a topology of the entire setup. That way they know the pods and their IPs on the other nodes. Weave creates its own bridge on the nodes and names it Weave, then assigns IP address to each network. The IPs shown here are just examples. In the upcoming practice test, you will figure out the exact range of IP addresses Weave assigns on each node. We will talk about IP address management and how IP addresses are handed out to pods and containers in the next lecture. Remember that a single pod may be attached to multiple bridge networks. For example, you could have a pod attached to the Weave bridge as well as the Docker bridge created by Docker. What path a packet takes to reach destination depends on the route configured on the container. Weave makes sure that pod gets the correct route configured to reach the agent, and the agent then takes care of other pods. Now, when a packet is sent from one pod to another on another node, Weave intercepts the packet and identifies that it's on a separate network. It then encapsulates this packet into a new one with new source and destination and sends it across the network. Once on the other side, the other Weave agent retrieves the packet, decapsulates it, and routes the packet to the right pod. So how do we deploy Weave on a Kubernetes cluster? Weave and Weave peers can be deployed as services or daemons on each node in the cluster manually, or if Kubernetes is set up already, then an easier way to do that is to deploy it as pods in the cluster. Once the base Kubernetes system is ready, with nodes and networking configured correctly between the nodes, and the basic control plane components are deployed, Weave can be deployed in the cluster with a single kubectl apply command. This deploys all the necessary components required for Weave in the cluster. Most importantly, the Weave peers are deployed as a daemon set. A daemon set ensures that one pod of the given kind is deployed on all nodes in the cluster. This works perfectly for the Weave peers. If you deployed your cluster with a kubeadm tool and Weave plugin, you can see the Weave peers as pods deployed on each node. For troubleshooting purpose, view the logs using the kubectl logs command. Well, that's it for this lecture. I will see you in the next.
So for the first question, it's asking us to inspect the kubelet service and identify the container runtime endpoint that's set for this Kubernetes cluster. So I'm going to do a ps-aux pipe grep -i kubelet. And we can see there's a lot of information, so I'm going to further drill that down. And so I'm going to grep for container-runtime. And we can see the --container-runtime-endpoint flag is set to unix://var run containerd.sock. So I will select this one. What is the path configured with all binaries of CNI supported plugins? So all of the plugins are going to be stored in /opt CNI bin. And so if I then do an ls, we can see all of the binaries here. So it's going to be /opt CNI bin. Identify which of the below plugins is not available in the list of available CNI plugins on the host. So let's see, VLAN. We have VLAN there. We have, let's see, Cisco. Do we have Cisco? Doesn't look like we have Cisco. Let's just double check if the other two are there. So Bridge. We've got Bridge, DHCP. We've got DHCP. So Cisco is not there. What is the CNI plugin configured to be used on this Kubernetes cluster? So to see that, we can just do a ls/etc CNI net.d. So this is going to tell us which plugin has been configured, and we can see it's Flannel. So I'll select Flannel. And what binary executable file will be run by the kubelet after a container and its associated namespaces are created? So if I cat that file, and let me actually move into there. Here we can see that the binary that it's going to run is Flannel, and then after that it's going to run port map. So the answer is Flannel. And that's going to match up with this binary here. So we'll say Flannel. And that's going to wrap up this lab. So for the first question, it says, in this practice test, we will install WeaveNet pod networking solution to the cluster. And it says, let's first inspect the setup. And so they've deployed an application called app in the default namespace. What is the state of the pod? So we'll do kubectl get pods. And we can see that it's stuck in container creating state. So we'll say it's not running. And it says, inspect why the pod is not running. So we'll just do a describe. And usually what I like to do is go to the events section, because that usually gives us some information as to what's going on. And I do see some errors. And you can see from the kubelet, it says failed to create pod sandbox. And it says failed to set up network for sandbox, unable to allocate IP addresses. So it looks like there's an issue with networking. So why is the pod not running? It looks like there's no network configured. And so it says to deploy the WeaveNet networking solution to the cluster. So it says they've provided the manifest file, but I'm going to kind of walk you through how to actually do this without if you didn't have it provided. So this involves taking a look at the documentation. So if you go to the Kubernetes documentation, there's this installing add-on section. So this is where you go to install the networking add-ons. And since we're going to install WeaveNet, just go ahead and click on this link. And installing WeaveNet is actually very simple. There's just this one command right here. So this will actually download the manifest file and apply it at the same time. But it's always good to take a look at all of the documentation because there's always little gotchas further down in the documentation that you may not see at first. And so as I was going through this, if we actually take a look and go down to the section on things to watch out for, it says if you do set the cluster CIDR option on kubeproxy, make sure it matches the IP-alloc range on WeaveNet. So to actually set up the IP-alloc range, you would just go to that manifest file, and under containers, you would pass an environment variable that says IP-alloc range and then the range that you're giving. So I'm going to copy this manifest. We're not going to apply it first because we're going to change a few things. So I'm just going to copy the URL. And I'm going to just do a curl. Sorry, not a curl, a wget. All right, and so we've got this file that we just copied. But remember, based off of the documentation, we need to set that IP-alloc range if our kubeproxy has the cluster CIDR option set. So on the kubeproxy process, we have to check if this flag is set. So we're going to go back to the cluster. And I'm going to do a kubectl get pods -n cube -system. So let's take a look at the kubeproxy. So if we go to kubeproxy, I'm going to do a kubectl describe pod kubeproxy. And so let's take a look at the configs. And so here the command we could see, okay, so it looks like the configs are loaded from this config.conf file. So this is going to be in /var/lib/kube-proxy. And if we take a look at the mounts, var lib kube-proxy comes from this volume called kube-proxy. So where does this kube-proxy come from? Well, let's go to the volumes, kube-proxy. This comes from a config map called kube-proxy. So what we have to do is take a look at the configs from that config map. So if I do kubectl get config map, right, we want this kube-proxy one. So I'll do same thing, but a describe. So this is going to be all of the configs for our kubeproxy, and we want to check for that cluster CIDR, see if that's been set. And I realized I put the wrong one in. We don't want, we want describe config map kube-proxy. There we go. So now we want to look for that cluster CIDR. Okay, so the cluster CIDR has been set. It's going to be this 10.244.0.0/16. So we're going to have to do the same thing by updating it in that documentation as well. So we have to have the network plugin actually know what CIDR range we're using. So I'm going to go in there. And I'm going to go down to the container. And let's go to the documentation to see where we set this. So there's an example here. So under containers, we have to look for the one called weave. So this is the init container. We want, here we go, container called weave. There's already some environment variables, so we're just going to set one at the top. Name and what, let's copy this. So this is going to be IP-alloc range. And then value. I think it was 10.244.0.0/16. We'll have to double check because I don't remember. And let's just double check one more time at the documentation. So that's all we should have to do. And if we go back just to double check, what was it? 10.244.0.0/16. So now we can do a kubectl apply -f weave -daemon set. All right. Now if I do a kubectl get pods -n cube-system, we can see that there's 2 weave pods running. That's going to be from the daemon set running on the 2 different nodes. So usually with these plugins, there's going to be one on each node, or in this case, I think there's only one, but that's all right. So here we can now do a kubectl get pod, and we can see that it is now running with no issues. And so we'll do a check, and we can see it's successfully installed, and that's going to wrap up this lab.
Hello and welcome to this lecture. In this lecture, we discuss about IP address management. So how does IP address management work in Kubernetes? This section does not concern the IP address assigned to the nodes in the network. You can manage that on your own or with your own external IPAM solutions. What this section covers is how are the virtual bridge networks in the nodes assigned an IP subnet, and how are the pods assigned an IP. Where is this information stored, and who is responsible for ensuring there are no duplicate IPs assigned? Let's start with the who. Let's ask CNI, as they're the ones who define the standards. CNI says it is the responsibility of the CNI plugin, the network solution provider, to take care of assigning IPs to the containers. Remember the basic plugin we built earlier? We actually took care of assigning IP addresses within this plugin. There was a section for assigning IP to the container network namespace, but how do we manage these IPs? Now, Kubernetes doesn't care how we do it. We just need to do it by making sure we don't assign any duplicate IPs and manage it properly. An easy way to do it is to store the list of IPs in a file and make sure we have necessary code in our script to manage this file properly. This file would be placed on each host and manages the IPs of pods on those nodes. Instead of coding that ourselves in our script, CNI comes with 2 built-in plugins to which you can outsource this task to. In this case, the plugin that implements the approach that we followed for managing the IP addresses locally on each host is the host local plugin. But it is still our responsibility to invoke that plugin in our script, or we can make our script dynamic to support different kinds of plugins. The CNI configuration file has a section called IPAM in which we can specify the type of plugin to be used, the subnet and routes to be used. These details can be read from our script to invoke the appropriate plugin instead of hard-coding it to use host local every time. Different network solution providers does it differently. Let's see how Weaveworks manages IP addresses. In fact, you have seen some of the IPs assigned by Weave in the previous practice test. Weave, by default, allocates the IP range 10.32.0.0/12 for the entire network. That gives the network IPs from range 10.32.0.1 to 10.47.255.254. That's about 1 million IPs that you can use for pods on the network. From this range, the peers decide to split the IP addresses equally between them and assigns one portion to each node. Pods created on these nodes will have IPs in this range. Of course, these ranges are configurable with additional options passed while deploying the Weave plugin to a cluster. Well, with this lecture, head over to the practice test and explore IPAM in the Weave CNI plugin.
So the first question is asking us how many nodes are part of this cluster. So we can just do a kubectl get nodes, and we can see that there's 2 nodes, one called control plane and one called node 1. Next question is asking us what is the networking solution used by this cluster. So to see the CNI configuration, we can go to /etc CNI net weave.d. And then here, if I do an ls, we can see the config file. You can see it's got the name weave, so that's probably going to be the answer, but let's go ahead and just cat this file just to double check. And here we can see the plugins. We've got the weave plugin, so the correct answer is going to be weave. How many weave agents are deployed in this cluster? So to do this, we're going to see the number of pods, weave pods that have been deployed. So we'll do a kubectl get pods, and then we'll do a -n cube-system because that's going to be the namespace that it gets installed in. And we can see here that there are 2 weave pods. And so the correct answer is going to be 2. On which nodes are these weave pairs present? Well, we can run the same exact command, but I'm just going to do a -o wide so we can see which nodes that they are running on. And if we take a look, the first weave, this is going to be running on control plane node, and the other one's going to be running on node 1. So the options we have on worker nodes only, that's not true. All on node 1, that's not true. All on master node, that's not true. One on every node. That's probably going to be the correct answer because we've got one running on the 2 nodes that we have. And then here we have 2 on master, 2 on worker, which is wrong. So we're going to select this one. Now it's asking us to identify the name of the bridge network interface created by Weave on each node. So here I'm going to do an IP address so that we could see all of the different IP interfaces on this box. And we'll go through here. We've got LO, we've got data path, and then here we can see one that's called Weave. So that's most likely going to be the interface that they're asking about. The next question is asking us, what is the pod IP address range configured by Weave? So to do this, what we're going to do is we're going to take a look at the logs for one of the Weave pods. And when it starts up, it's going to give us the information as to what address range Weave, the plugin, is actually using. So we'll do a kubectl get pods again. And I'm going to get the name of one of the pods. So I'll just grab this one. And now I'll do kubectl logs. And we'll get the logs from that specific pod. And I'm going to scroll up to the top. And we're going to take a look. And we should see a log message where it prints out some information. And we're going to specifically look for IP alloc range. So this is going to be the pod IP address range, and we can see it's set to 10.244.0.0/16. So I will select that. And the final question is asking us, what is the default gateway configured on the pods scheduled on node 1? So anytime a pod's deployed, what is going to be the IP address of the default gateway for that specific pod? And the easiest way to figure this out is just to deploy a pod onto node 1 and then just log in and just run IP route to see what is the default gateway. And so to do that, I'm going to run kubectl run, and I'm just going to deploy a dummy container. So I'm going to use the busybox container. So I'll call this pod busybox. And the image, we're going to use busybox. And I'm going to do a --dry -run equals client because I want to print out the configuration and not immediately run it. And we'll print it out in YAML. And the command I want to run is we'll just do sleep 1000. And I'm going to just output this to a file because I'm going to make some changes because we need to make sure we deploy to node 1. So here we've got that printed out. Let me do ls. Okay, so we've got busybox. I'm going to open this up. And under spec, I'm going to add this line here, and we're going to add in node name, and this is going to deploy this pod on a specific node, and we want to deploy this on node 1. We'll save this, and I'm going to do a kubectl apply, and then we'll apply that configuration. All right, so the pod's been created. Let's do a kubectl get pods. Let's make sure it's running. Okay, so the pod's running, and now we have to just run a command in the pod. So I can just do a kubectl exec, and then the pod that I want to run this command in, so busybox. And then we'll do a --, and then we just specify the command we want to run. So if you want to see the default gateway or any of the routes, you just do IP route. And if you look at the default route, that's going to be starting with default. So it says default via this specific IP address, so 10.244.192.0. So we're going to select that one. And that's going to wrap up this lab.
Hello and welcome to this lecture. In this lecture, we will discuss about service networking. In the previous lectures, we talked about pod networking, how bridge networks are created within each node, and how pods get a namespace created for them, and how interfaces are attached to those namespaces, and how pods get an IP address assigned to them within the subnet assigned for that node. And we also saw through routes or other overlay techniques, we can get the pods in different nodes to talk to each other, forming a large virtual network where all pods can reach each other. Now, you would rarely configure your pods to communicate directly with each other. If you want a pod to access services hosted on another pod, you would always use a service. Let's quickly recap the different kinds of services. To make the orange pod accessible to the blue pod, we create an orange service. The orange service gets an IP address and a name assigned to it. The blue pod can now access the orange pod through the orange service's IP or its name. We'll talk about name resolution in the upcoming lectures. For now, let's just focus on IP addresses. The blue and orange pod are on the same node. What about access from the other pods on other nodes? When a service is created, it is accessible from all pods on the cluster, irrespective of what nodes the pods are on. While a pod is hosted on a node, a service is hosted across the cluster. It is not bound to a specific node. But remember, the service is only accessible from within the cluster. This type of service is known as cluster IP. If the orange pod was hosting a database application that is to be only accessed from within the cluster, then this type of service works just fine. Say, for instance, the purple pod was hosting a web application. To make the application on the pod accessible outside the cluster, we create another service of type node port. This service also gets an IP address assigned to it and works just like cluster IP. As in, all the other pods can access this service using its IP. But in addition, it also exposes the application on a port on all nodes in the cluster. That way, external users or applications have access to the service. So that's the topic of our discussion for this lecture. Our focus is more on services and less on pods. How are the services getting these IP addresses, and how are they made available across all the nodes in the cluster? How is the service made available to external users through a port on each node? Who is doing that, and how and where do we see it? So let's get started. Let's start on a clean slate. We have a 3-node cluster, no pods or services yet. We know that every Kubernetes node runs a kubelet process, which is responsible for creating pods. Each kubelet service on each node watches the changes in the cluster through the kubeAPI server, and every time a new pod is to be created, it creates the pod on the nodes. It then invokes the CNI plugin to configure networking for that pod. Similarly, each node runs another component known as kubeproxy. kubeproxy watches the changes in the cluster through kubeAPI server, and every time a new service is to be created, kubeproxy gets into action. Unlike pods, services are not created on each node or assigned to each node. Services are a cluster-wide concept. They exist across all the nodes in the cluster. As a matter of fact, they don't exist at all. There is no server or service really listening on the IP of the service. We have seen that pods have containers, and containers have namespaces with interfaces and IPs assigned to those interfaces. With services, nothing like that exists. There are no processes or namespaces or interfaces for a service. It's just a virtual object. Then how do they get an IP address, and how are we able to access the application on the pod through service? When we create a service object in Kubernetes, it is assigned an IP address from a predefined range. The kubeproxy components running on each node gets that IP address and creates forwarding rules on each node in the cluster, saying any traffic coming to this IP, the IP of the service, should go to the IP of the pod. Once that is in place, whenever a pod tries to reach the IP of the service, it is forwarded to the pod's IP address, which is accessible from any node in the cluster. Now remember, it's not just the IP, it's an IP and port combination. Whenever services are created or deleted, the kubeproxy component creates or deletes these rules. So how are these rules created? Kubeproxy supports different ways, such as user space, where kubeproxy listens on a port for each service and proxies connections to the pods by creating IPVS rules, or the third and the default option, and the one familiar to us, is using IP tables. The proxy mode can be set using the proxy mode option while configuring the kubeproxy service. If this is not set, it defaults to IP tables. So we'll see how IP tables are configured by kubeproxy and how you can view them on the nodes. We have a pod named DB deployed on node 1. It has IP address 10.244.1.2. We create a service of type cluster IP to make this pod available within the cluster. When the service is created, Kubernetes assigns an IP address to it. It is set to 10.103.132.104. This range is specified in the Kube API server's option called Service Cluster IP Range, which is by default set to 10.0.0.0/24. In my case, if I look at my Kube API server option, I see it is set to 10.96.0.0/12. That gives my services IP anywhere from 10.96.0.0 to 10.111.255.255. A relative point to mention here, when I set up my pod networking, I provided a pod network CIDR range of 10.244.0.0/16, which gives my pods IP addresses from 10.244.0.0 to 10.244.255.255. The reason I brought this up here is because whatever range you specify for each of these networks, it shouldn't overlap, which it doesn't in this case. Both of these should have its own dedicated range of IPs to work with. There shouldn't be a case where a pod and a service are assigned the same IP address. So getting back to services, that's how my service got an IP address of 10.103.132.104. You can see the rules created by kubeproxy in the IP table's NAT table output. Search for the name of the service, as all rules created by kubeproxy have a comment with the name of the service on it. These rules mean any traffic going to the IP address 10.103.132.104 on port 3306, which is the IP of the service, should have its destination address changed to 10.244.1.2 and port 3306, which is the IP of the pod. This is done by adding a DNAT rule to IP tables. Similarly, when you create a services of type node port, kubeproxy creates IP table rules to forward all traffic coming on a port on all nodes to the respective backend pods. You can also see kubeproxy create these entries in the kubeproxy logs itself. In the logs, you will find what proxier it uses, in this case it's IP tables, and then adds an entry when it added a new service for the database. Note that the location of this file might vary depending on your installation. If you don't see these entries, you must also check the verbosity level of the process as well. Well, that's it about service networking. I will see you in the next lecture.
So the first question is asking us, what network range are the nodes in the cluster a part of? So what this is asking is, what is the IP address of the nodes? So not the pods or the services, but the nodes itself. So what I'm going to do is I'm going to do a kubectl get nodes dash o, and I'm going to do wide. And I'm going to look for the internal IP of my nodes. So I'm on the control plane, so 192.16.10.10. And so now if I take a look at the interfaces on this node, I could do an IP add. And we're going to see all of the interfaces. And so if we go down to Ethernet 0 or Ethernet 1, we want to look for whichever interface has this IP address, which is Ethernet 0, which has 192.6.10.10. So the subnet is going to be 192.168.10.0/24. 24 means that the last 8 bits, so the last octet, is going to be reserved for the host addresses. So we want 192.6.10.0/24. So that's what all of the nodes are going to be using. What is the range of IP addresses configured for pods on this cluster? So first of all, we have to see what we're doing from a networking perspective. And so I'm going to just do a kubectl get all all namespaces just to see everything that's deployed. And if we look at the kube system namespace, we can see that we have a weave pod. So for networking, we're using weave. So I'm actually going to take a look at the logs of that pod to see if it's going to give us some information about what IP addresses are going to be used for the pods in our cluster. So I'll do a kubectl logs. I'll grab one of the weave pods. And I'm just going to start at the top and just kind of scroll my way down until I see a log message that tells us what subnet's going to use. And what we want to do is look for something like ipalloc for IP allocation. And we can see ipalloc range 10.1244.0.0/16. So any pods that you deploy, they're going to be part of this subnet here. So the answer is 10.244.0.0/16. Now the next question is asking, what is the IP range configured for the services within the cluster? And to see the IP address range for services, what we want to do is take a look at the configuration of the API server. So the API server, its manifests are going to be located in /etc. I think it's Kubernetes manifests. And we're going to look at the kube API server. And I'm going to go to the top, and there should be a certain flag that specifies the service range or the IP address range for the services. And here we go, service cluster IP range, which is 10.96.0.0/12. Next question is asking us how many kube proxy pods are deployed in this cluster. So I'm going to do a kubectl get pods -n kube -system. We could see that we have 2 kube proxy pods. So I'll select 2. What type of proxy is the kube proxy configured to use? Well, for this, let's take a look at the kube proxy pods themselves and let's see if the logs tell us anything. So I'll do kubectl logs, and I'll grab one of these pods. And I'm just going to look through the logs to see if it tells us what type of proxy it's using. So detecting node IP address, using IP tables proxy. Okay, so this is probably the answer right here, using IP tables proxy. So let's select IP tables. And finally, it's asking, how does the Kubernetes cluster ensure that the kube proxy pod runs on all nodes in the cluster? Now, just knowing based off of this question, what is the methodology that we use to normally deploy on every single node in a cluster? Usually it's a daemon set, but let's confirm that's the case. So I'm going to do a kubectl get all --all namespaces, and I'm just going to look for anything with kube proxy. So obviously under pods, I see the kube proxies. That's fine. Under services, there's nothing there. Under daemon set, looks like we do have a kube proxy.
Hello and welcome to this lecture. In this lecture, we will discuss about DNS in the Kubernetes cluster. If you are new to DNS, make sure you go through the prerequisite section on DNS where we discuss what DNS is, what are the tools used for working with DNS such as host, NSLOOKUP, and the dig utility, and the different types of DNS records like A, CNAME, etc. And we also saw how to set up our own DNS server using Core DNS. In this lecture, we will see what names are assigned to what objects, what are service DNS records, pod DNS records, what are the different ways you can reach one pod from another, and in the next lecture, we will see how Kubernetes implements DNS in the cluster. So we have a 3-node Kubernetes cluster with some pods and services deployed on them. Each node has a node name and IP address assigned to it. The node names and IP addresses of the cluster are probably registered in a DNS server in your organization. Now, how that is managed, who accesses them, are not of concern in this lecture. In this lecture, we discuss about DNS resolution within the cluster, between the different components in the cluster, such as pods and services. Kubernetes deploys a built-in DNS server by default when you set up a cluster. If you set up Kubernetes manually, then you do it by yourself. We will see how that is done and how it is configured in the next lecture. As far as this lecture is concerned, we will see how it helps pods resolve other pods and services within the cluster. So we don't really care about nodes. We focus purely on pods and services within the cluster. As long as our cluster networking is set up correctly, following the best practices we learned so far in this section, and all pods and services can get their own IP address and can reach each other, we should be good. Let's start with just 2 pods and a service. I have a test pod on the left with the IP set to 10.244.1.5, and I have a web pod on the right with the IP set to 10.244.2.5. Looking at their IPs, you can guess that they're probably hosted on 2 different nodes, but that doesn't really matter. As far as DNS is concerned, we assume that all pods and services can reach each other using their IP addresses. To make the web server accessible to the test pod, we create a service. We name it Web Service. The service gets an IP 10.107.37.188. Whenever a service is created, the Kubernetes DNS service creates a record for the service. It maps the service name to the IP address. So within the cluster, any pod can now reach this service using its service name. Remember, we talked about namespaces earlier, that everyone within a namespace address each other just with their first names, and to address anyone in another namespace, you use their full names. In this case, since the test pod and the web pod and its associated service are all in the same namespace, the default namespace, you are able to simply reach the web service from the test pod using just the service name web-service. Let's assume the web service was in a separate namespace named apps. Then, to refer to it from the default namespace, you would have to say webservice.apps. The last name of the service is now the name of the namespace. So here, web service is the name of the service and apps is the name of the namespace. For each namespace, the DNS server creates a subdomain. All the services are grouped together into another subdomain called SVC. So what was that about? Let's take a closer look. Web service is the name of the service and apps is the name of the namespace. For each namespace, the DNS server creates a subdomain with its name. All pods and services for a namespace are thus grouped together within a subdomain in the name of the namespace. All the services are further grouped together into another subdomain called SVC. So you can reach your application with the name webservice.apps.svc. Finally, all the services and pods are grouped together into a root domain for the cluster, which is set to cluster.local by default. So you can access the service using the URL webservice.apps.svc.cluster.local. And that's the fully qualified domain name for the service. So that's how services are resolved within the cluster. What about pods? Records for pods are not created by default, but we can enable that explicitly. We will see that in the next lecture. Once enabled, records are created for pods as well. It does not use the pod name though. For each pod, Kubernetes generates a name by replacing the dots in the IP address with dashes. The namespace remains the same and type is set to pod. The root domain is always cluster.local. Similarly, the test pod in the default namespace gets a record in the DNS server with its IP converted to a dashed hostname, 10-244-1-5, and namespace set to default. Type is pod, and the root is cluster.local. This resolves to the IP address of the pod. Hello and welcome to this lecture. In this lecture, we will discuss how Kubernetes implements DNS in the cluster. In the previous lecture, we saw how you can address a service or pod from another pod. In this lecture, we will see how Kubernetes makes that possible. Say you were given two pods with two IP addresses. How would you do it? Based on what we learned in the prerequisite lectures on DNS, an easy way to get them to resolve each other is to add an entry into each of their etc hosts file. On the first pod, I would say the second pod, web, is at 10.244.2.5, and on the second pod, I would say the first pod, test, is at 10.244.1.5. But of course, when you have thousands of pods in the cluster and hundreds of them being created and deleted every minute, this is not a suitable solution. So we move these entries into a central DNS server. We then point these pods to the DNS server by adding an entry into their etc resolve.conf file, specifying that the name server is at the IP address of the DNS server, which happens to be 10.96.0.10 in this case. Every time a new pod is created, we add a record in the DNS server for that pod so that other pods can access the new pod and configure the etc resolve.conf file in the pod to point to the DNS server so that the new pod can resolve other pods in the cluster. This is kind of how Kubernetes does it, except that it does not create similar entries for pods to map pod name to its IP address as we have seen in the previous lecture. It does that for services. For pods, it forms host names by replacing dots with dashes in the IP address of the pod. Kubernetes implements DNS in the same way. It deploys a DNS server within the cluster. Prior to version 1.12, the DNS server implemented by Kubernetes was known as kubedns. With Kubernetes version 1.12, the recommended DNS server is CoreDNS. We took a brief look at CoreDNS in one of the prerequisite lectures. So how is the CoreDNS setup in the cluster? The CoreDNS server is deployed as a pod in the kubesystem namespace in the Kubernetes cluster. Well, they are deployed as two pods for redundancy as part of a replica set. They're actually a replica set within a deployment, but it doesn't really matter. But we'll just see CoreDNS as a pod in this lecture. This pod runs the CoreDNS executable, the same executable that we ran when we deployed CoreDNS ourselves. CoreDNS requires a configuration file. In our case, we used a file named corefile. So does Kubernetes. It uses a file named corefile located at etc CoreDNS. Within this file, you have a number of plugins configured, the ones highlighted in orange. Plugins are configured for handling errors, reporting health, monitoring metrics, cache, etc. The plugin that makes CoreDNS work with Kubernetes is the Kubernetes plugin, and that is where the top-level domain name of the cluster is set. In this case, cluster.local. So every record in the CoreDNS DNS server falls under this domain. With the Kubernetes plugin, there are multiple options. The pods option you can see here is what is responsible for creating a record for pods in the cluster. Remember, we talked about a record being created for each pod by converting the IPs into the dashed format. That's disabled by default, but it can be enabled with this entry here. Any record that the DNS server can't solve, for example, say a pod tries to reach www.google.com, it is forwarded to the name server specified in the CoreDNS pod's etc resolve.conf file. The etc resolve.conf file is set to use the name server from the Kubernetes node. Also note that this core file is passed in to the pod as a config map object. That way, if you need to modify this configuration, you can edit the config map object. We now have the core DNS pod up and running using the appropriate Kubernetes plugin. It watches the Kubernetes cluster for new pods or services, and every time a pod or a service is created, it adds a record for it in its database. Next step is for the pods to point to the core DNS server. What address do the pods use to reach the DNS server? When we deploy the core DNS solution, it also creates a service to make it available to other components within the cluster. The service is named as kubedns by default. The IP address of this service is configured as the name server on pods. Now, you don't have to configure this yourself. The DNS configurations on pods are done by Kubernetes automatically when the pods are created. Want to guess which Kubernetes component is responsible for that? The kubelet. If you look at the config file of the kubelet, you will see the IP of the DNS server and domain in it. Once the pods are configured with the right name server, you can now resolve other pods and services. You can access the web service using just web service or web service.default or web service.default.svc or web service.default.svc.cluster.local. If you try to manually look up the web service using nslookup or the host web service command, it will return the fully qualified domain name of the web service, which happens to be web-service.default.svc.cluster.local. But you didn't ask for that, you just said web service. So how did it look up for the full name? It so happens the resolve.conf file also has a search entry which is set to default.service.cluster.local as well as svc.cluster.local and cluster.local. This allows you to find the service using any name, web service or web service.default or web service.default.svc. However, note that it only has search entries for service, so you won't be able to reach a pod the same way. For that, you need to specify the full FQDN of the pod. Well, that's it for this lecture. Head over to the practice test and practice working with DNS on a Kubernetes cluster. I will see you in the next lecture.